everyone. This is 5.2, which is a discussion on the definite integral. There's a lot to discuss here, so let's get right to it. So the definite integral from a to b of f of x dx is defined to be this limit. Basically, it's just the area under the curve that we saw from 5.1. We've kind of developed a better language here. Instead of just calling it a for area, we're actually developing some notation. So I say that this is the area under the curve, quote unquote under, which we'll discuss shortly, under the curve of f of x on the closed interval a to b. When the limit exists, we say that f is integrable on a to b, kind of like we use the word differentiable if the tangent line exists, and so on. Now here I note that the integral from a to b of f of x dx may be negative, and we'll see that shortly as well with this visualization. And here what this is defined to be is this limit. It's a summation basically representing the area under the curve, just like we formulated in 5.1. Now this x of I star, you don't really have to worry about too much. I describe it here a bit. Delta x is the same as before, it's b minus a all over n, so that's the width of those rectangles. X of I star is supposed to be a generalization of what we saw x of I to be in 5.1. We saw x of I to be either the left or right endpoints, but here x of I star is just any value in between in the subinterval x of I minus 1 to x of I, where x of I is what we saw earlier, a plus I delta x. So basically you just pick some random point in between that's your so-called sample point, and when you project that to the function you get a height, multiply that by delta x the width, you get the area of the rectangle, sum over n many rectangles, and then take the limit as n goes to infinity, you get the exact area under the curve. Now, since f of x could be below the x-axis, kind of like we see over here, then that height would represent a negative value, so you actually get a negative rectangular area here. So what this really means is that areas that are below the curve will represent a negative area, whereas areas above the curve will represent a positive area, actually. So that's pretty important to note, I think. So with that being said, the way we're defining integral here, the definite integral could actually be negative, it could even be 0 if these all cancel out exactly. You can kind of think of that, of it that way anyways. Now as far as the language goes, so this dx we'll kind of talk about a little later, but it relates very much to this delta x here. In fact, a lot of the language from these Greek letters to these Roman letters, there's some parallels, of course. Delta is the Greek D, and sigma is the Greek S for some, of course. Yeah, I guess we use delta to mean like the difference between. It's a small change in. Delta usually just means change in. But change in value is really the difference in values. Now, this function that we're so-called integrating from a to b is known as the integrand. Kind of think of the inside of the radical as the radicand. The inside of the integral is the integrand. So you always have dx and the integral. So the function that's in between the integral and the dx, that's your function that you're integrating. The limits of integration are these values a and b. So I'll just call these limits, but they're limits of integration really, is I guess the complete verbiage. And b would be, of course, be the upper limit and a is the lower limit, but that's all I'm going to say there, I think, as far as that goes. And yeah, so with that being said, now we can look at some properties of the integral. Maybe we'll do some examples, but to be quite honest, at this level for 5.2, the examples we'll be seeing of actually finding a integral would kind of be similar to what we saw in 5.1, where we have to consider these weird sums. We'll still do it though, and we'll actually see some properties beforehand though that'll help us develop some different techniques to find integrals based on previous knowledge, basically. So let's take a look at that right now and see how far it goes. Right, so here I've listed some properties of the integral in no particular order, and I want to do my best to explain why these are true through a visualization of the area under the curve. Because again, that's what the definite integral really represents, is the area under the curve of f of x from a to b. And with that one exception that it could be below where we consider that area to be negative. So here we say the integral from a to b of f of x is negative the integral from b to a of f of x dx. Now this is a little hard to show visually, but normally we consider a to be smaller than b. So we're going from x equals a to x equals b under the curve like this. But what if we wanted to go from b to a, would that necessarily mean that the area is negative? Well, kind of actually, because notice that this integral is defined on a limit that's, well, basically dependent on delta x and f of x of I, where the x of I is also dependent on delta x. But notice delta x what? Delta x is what? Delta x is b minus a all over n. But if we're going, instead of from a to b, if we're going from b to a, then these would actually swap, and a minus b would just be negative b minus a in that case. So notice if you swap a difference, you get negative the result you would have gotten otherwise. So this is for the usual case, but for this particular instance, the delta x we'd be using would be equal to a minus b over n. But if, again, if a is bigger than b, or even if a isn't bigger than b, it doesn't really matter, because notice this is just equal literally to negative b minus a all over n. So in actuality, we're not really using the fact that a is less than b in this case. This fact is true no matter what. It's just literally this kind of difference swap that happens. So that's the reason why this first guy is true. So if you swap the limits, what you can do, you just get negative of what you would have gotten otherwise. So it has very much of this kind of difference feel, that if you take a different way, you get negative of what you would have gotten otherwise. Okay. So now, for the next property here, this says that the area under the curve from A to A is 0. That makes a lot of sense because there's actually no area there. If you're under the curve and you're going from A to A, it's just a thin line, there's no area, because delta x is 0 in that case. And remember, since we're taking it to infinity, delta x goes to 0. So a 0 with rectangle has area 0, actually. So that makes sense. Now, what about this one? Well, here the function is a very particular function. It's the function f of x equals c. So in this case, the image we actually get is the area under the graph from x equals a to x equals b of f of x equals c. So really we're looking at the curve y equals c. So it's like this, so y is just some constant. And notice what we get here is just a rectangle, and its area is literally the height c multiplied by the width, which is b minus a, the difference between b and a, the distance from a to b. So it's literally just c times b minus a. So that I think is pretty easy to see visually. This one is not too hard to see visually. If you add two functions, you basically get kind of this, this height difference. That's actually not really the best way of seeing it though. So this is hard to explain visually, honestly. But it's very, very easy to explain based on the summation definition of definite integral. Because remember that we saw earlier, as far as summation properties go, the sum of a function over n, so sum of a sub n plus b sub n, is the sum of a sub n plus the sum of b sub n. So basically, since these integrals are kind of like summations, you can actually take them apart summation-wise. The same is true if it was negative. So if you had actually the difference of functions, the integral of the difference is the difference of the integrals. So this property, I think, is carried over from the summation counterpart of the integral. So basically from the summation definition, those properties carry over. So they're kind of like inherited. Similarly, for constants, constants can be pulled out of the sum. We saw this as factoring out. Same thing kind of happens here. But again, it's only constant multiples. So if you have a constant multiplied by a function of x, you can pull it out of the integral. This last one is also, well, unlike these two, I guess. This one is actually pretty simple to explain visually. Basically, if you have some value c that lies in between a and b, so let me just go back to this here and modify this a little bit. So let's say we have some function f that we're finding the area under the curve of, and we have some value c that lies somewhere in between a and b. Then notice that this area from a to b is literally just the area from a to c plus the area from c to b. So we can just split it up by some intermediate value. And there are some other properties that I think we may take a look at right now. They actually involve kind of comparing two functions, depending if you know which one's larger than the other. Right, so I said we may go over them because in my opinion, they're not as important or significant in the grand scheme of things, but we'll still talk about them a little bit. They're not super difficult to understand. They're the so-called comparison properties of the integral. And the first one basically says that if f of x is positive on the interval a to b, then the integral from a to b of f of x dx is positive. That just means that the function is above the x-axis, positive x values, then the area is positive. So that makes sense. And similarly, if it was negative, then it would be negative. Okay. If f of x is bigger than g of x on an interval, then the integrals are in the same order in that inequality. So the integral of f of x is bigger than or equal to the integral of g of x. This makes total sense because if f is above g for every value in between a and b, right, like it may not be the case outside of the interval, but if it's true there, then clearly the area under f is going to be larger than the area under g. That I think makes total sense visually. Like this area is larger than this area. In fact, one can say that the smaller area is contained literally in the larger area. And this one is actually kind of, I guess you could say, an application of the previous idea. If you have these kind of, this three-part inequality, m is less than or equal to f of x is less than or equal to capital M, we basically have these so-called bounds, upper bound and lower bound, of a function f from an interval a to b, or in the interval a to b, I should say. There we go. Then it is, I think, fairly obvious for similar reasons that the area, area under m is larger than the area under f, and the area under f is larger than the area under m. So in fact, notice that the area under m from a to b is literally just m times the quantity b minus a from one of the previous properties we saw, similarly for this lowercase m. So if you have a bound of functions, then you have a bound of the integrals. So that's really what all of these kind of say. They're kind of saying the same thing. And again, they're not going to be used too often, but at least we've seen them here. Right, so finally we're going to see an example, and I'm going to try to use this property as much as I can. I want us to recall these summation results we saw from 5.1. And I think something I should mention here is that when we convert this to a sum, that sum, the limit as n goes to infinity, that thing, that's known as a Riemann sum. So it's named after the mathematician Bernard Riemann, and he did a lot in mathematics. Obviously, a lot of these people that are named after, that things are named after them, have accomplished quite a bit in mathematics as a whole. So here I'm going to convert this into a Riemann sum. So to do that, notice f of x is x squared minus 3x plus 1. We have our a and b limits, 0 and 3. We need delta x, which is 3 minus 0 over n. So we're not estimating here. If we were, then n would be given. Let's say we want to estimate with, 5 rectangles or something like that. And then it would be given if we want to use right endpoints or left endpoints, or you can even use midpoints actually. But it's not something I want to focus on too much. And beyond that, let's find x sub I. So here I'm going to be taking really the general right endpoint estimate, but then take the limit as n goes to infinity. So I'm going to find I guess you'd call this a right sum. So let's see if we can do that here. So this is, remember it's a plus I delta x, so it's 0 plus I times this guy. So let me just write it as 3i over n if you don't mind. And notice that's just 3i over n, so that's not too bad. And in fact, let me collapse this a little bit. So this is just 3 minus 0, which is 3 over n. Good. And let me write this here so I have more space. Awesome. So now we'll continue to actually write the Riemann sum. So the Riemann sum then is the sum as I goes from 1 to n of f of x sub I, so f of 3i over n times delta x, which is 3 over n. And we can plug this into f and then go from there. But something that I kind of want to do before we actually get to that point is I want to split up the sum beforehand. Because if we plug in 3i over n into x, we'll get kind of this three-term thing we can take the sum over. But, and of course this is limit as n goes to infinity. At the very end, we'll do that part. So I don't want to worry about the limit right now too much anyways. And this is going to be actually the integral. What I want to do beforehand is apply some of those limit properties that we spent so much time talking about. So let's see if we can apply those here. So the first thing I'm going to apply is the summation property, which says we can split it apart amongst its terms. Like this. The second property I want to use is pulling out any constant multiples, and then applies to this 3 here. So I guess that's okay. And beyond that, you know what we can actually do is we can, well, for 1, notice since 1's a constant, the integral here is literally just 1 times the difference of the limits. So that's just 3. So that part's pretty nice. We have part of it solved. But now these will be our new f of x's, so to speak. So this we can call f of x, or f1 if you like, and this we can call f2 if you like. So in reality here I'm using this for f1 and for f2 individually. Because notice delta x is not changing because it's dependent on the limits. X sub i's are not changing because those again are dependent on the limits. So really I'm going to apply this for each f1 and f2. So I hope that's not too confusing. But let's see. So when we plug in 3i over n into x squared, we get, well, 9i squared over n squared times 3 over n, like that. And this is the sum from I equals 1 to infinity. That's a pretty bad looking sum. There we go, that looks better. And now notice we can pull out constants from this summation. 3 over n cubed, in fact this is really 27 over n cubed. That's constant in the sense that it's independent of our index I. And what we have left on the inside is just I squared. So that's good. So we'll take the limit as n goes to infinity for this guy. And notice that this sum right here, we really is just one of these. So it's these things that I recalled earlier, that I wrote down earlier anyways. So it's n times n plus 1 times 2n plus 1 all over 6. And again, we discussed these in greater detail in the previous video 5.1. And remember what we also discussed is that what happens here is that you can split this up, and we actually end up getting, so I'll kind of spare you the details if you don't mind, but what we actually get is, so it's 27 times, so let's see, that's going to be, it was I believe 2n squared plus 3n plus 1, but then distributing that n on the outside ups the power by 1. So it's 2n cubed plus 3n squared plus n. And each of these divided by 6 and divided by this n cubed. So divided by 6n cubed. So really I just kind of skipped out on the foiling part. Perfect. And of course these each reduce. And what do they reduce to? Well, I'm not going to actually erase too much as we go along. Let me just write the result over here maybe. So we get 27 times what? Well, this reduces to 1 over 3. This reduces to 1 over 2n. And this reduces to 1 over 6n squared. Now again, we're still technically in the limit as n goes to infinity. And I think that's a good place to stop this because notice that as n goes to infinity of this expression, well, the 27 is fine. But what really happens is that these guys here go to 0 in the limit because their denominator is approaching infinity. So really what we have left over is 27 over 3, which is 9. So that means this first integral here is just 9. Nice. Perfect. What about this one? Well, let's find out. So what I'm going to do now is I'm going to kind of erase this and kind of use things as I go along. So we already worked with the first one. Now for the second one, if we're just using x instead of x squared, then plugging 3i over n into x is literally just going to give us 3i over n, just like that. Now if we pull out constants, notice 9, 3 times 3 and n squared come out. So this is 9 over n squared opposed to the 27 over n cubed from the first integral. Good. And this is no longer I squared, but now just I. Now this is great because we have a formula for that, and that is, well, n times the quantity n plus 1 all over 2. So if we distribute that n, we get n squared plus n. They're each over 2, so it's n squared over 2 plus n over 2. But then we're dividing by n squared. We get n multiplied by what? Well, let's see. It's going to be n squared over 2n squared plus n over 2n squared. And notice after canceling some things, this 9 stays the same, kind of like this 27 was the same here. So I hope it isn't too confusing that I'm kind of erasing as we go along. I think it's a good idea, honestly, to do that because we're using this as a template to kind of handle a similar kind of question. So now this inside part here is, well, then reduces, of course, to 1 over 2 plus 1 over 2n. And 1 over 2n has an n in the denominator, and of course as n goes to infinity, that term goes to 0. So really just what we're left with really here is just 9 over 2. Awesome. So this is equal to 9 over 2 in the limit. So this guy is 9 over 2, which I'll write in red. Or 4.5 if you like, but that's fine. And this we saw was 3. So notice we're doing 9 minus 3 times this quantity plus that quantity. So the 9 plus 3 is just 12. So altogether, this integral is equal to, so I'm going to kind of box and border this off a little bit. So we end up getting really is this work here. So that's equal to this, and let me border that work off. There we go, it looks a little better, I think. So we end up with 9 minus 27 over 2 plus 3, the 9 plus 3 part's 12. You can write 12 actually as, let me see if this is okay. Yeah, so we can actually write the 12 as 24 over 2. So 24 over 2 minus 27 over 2 is really negative 3 over 2. Which is weird because it's negative, but remember it's not weird because what this means is that it's mostly in the negative region. In fact, I'm going to graph this right now just to show us that's the case, and then that'll be the end for this video. Right, so I've just basically created a table here to kind of assist me in graphing. This is of course going to be an upward parabola, so I just wanted to pick some points between 0 and 3. So I plugged in 0, 1, 2, and 3, and I got these values, 1, negative, 1, negative, 1, and 1. And that actually tells us that the vertex is going to be actually halfway between these, which is 3 over 2. And clearly you can tell using calculus that if you take derivative of this, you get 2x minus 3. Setting that equal to 0 will actually result in x being equal to 3 halves, which is where we have a horizontal tangent line because its derivative is legitimately 0 there. And that's right here at 3 halves. And if you plug it in, you get actually 1 1/4, which is about here. And notice that the image you get is something like this. Now notice that the area is mostly negative. It's mostly below the x-axis. So again, just to show that, let me try to emphasize on this a little more and shade some things. But we have these two that are positive areas, but then we have this great negative area below. So visually it makes sense actually that of course if the scale is correct, that the definite integral in this case of this function is indeed negative because it appears to mostly be below the x-axis in this region. So again, this is a positive value, this is a big negative value, and this is a positive value. So it's not all negative, but it's mostly negative, so that makes the integral negative. Great. So I haven't done too many examples in this section, and I'll be honest about that, but of course, we have seen some properties that will prove useful in the following sections. We saw some of the properties applied here. To be quite honest, we won't really use them too much, but at least we've seen them here, and we'll see them applied more in 5.3. Finally, we'll get to see the link between the area under the curve, indefinite integrals, and antiderivatives. And it's one of the biggest highlights in calculus, and it's really magical and beautiful. You'll all love it, I promise. So again, we'll discuss more of that in the next sections coming. We'll see a lot of that after 5.3 as well. That's really where we start to separate these conceptual discussions in 5.1 and 5.2 to more technical discussions where we'll actually see some technique and more examples finally. So I'll see you in the videos for that. Hope you enjoyed this, and I'll see you then.